folks. I'm Doug Jones with Danley Sound Labs. Today I want to talk with you a little bit about our synergy horn. You know, as you probably know by now, the only thing we make is horns. We believe in horns. We think it's a better mousetrap, if you will. Well, a better loudspeaker. So you might say, well, why horns? Because everybody knows that horns have problems, right? They honk, there's distortion. Why did we decide to go back to this old technology? Well, I think to answer that question, it might be worthwhile to think back in time a little bit. No, Tom, we're not going back in time. We're thinking about going back in time.
Man, you're no fun.
Maybe next time. All right, so if we think about going back in time, back when the movies were learning how to talk, you know, power was a big deal. Amplifiers were small, loudspeakers were very inefficient. It took a lot of power to create any amount of sound pressure levels. So efficiency was really what drove things. And people realized that the horn was probably the most efficient way to couple this moving mass, we call it a transducer or a diaphragm, to the air, to get that transference of the vibration from one element to another. The problem is that in order to optimize that transfer, if you will, it had to be done in a very narrow bandwidth. So horns got this stigma, I suppose, this reputation, and maybe well deserved, as devices that just didn't sound that good. Yeah, they were efficient, boy, and they sent the sound where it needed to go, but they just didn't have fidelity. Now, of course, over the years, the definition of fidelity has changed. If you go back and look at some of the spec sheets from the 1920s and 30s of those early loudspeakers, you see, full fidelity devices that went all the way up to 5 kilohertz because this was a big deal. We've come a long way since then. So back to our story. The horn, was popular for a while, but people became dissatisfied with all of the drawbacks. They became dissatisfied with the limited bandwidth, with the distortion that's inherent when you take, like down in the neck of a horn where there's a large amount of constriction and you're putting a lot of pressure through there. Harmonic distortion is naturally created. Now, just to back up a little bit here, what's the big deal about bandwidth? Well, one of the things that makes our business, audio, so incredibly difficult and, in my view, fascinating, is this enormous bandwidth that we have to contend with. Vision has not even a 2-to-1 ratio between the longest wavelength that our eyes can perceive and the shortest. Our auditory system, on the other hand, has a 1,000-to-1 ratio of wavelengths that it has to contend with. So if we're going to build a device that accurately reproduces sound over the entire audible range, we have to deal with wavelengths that are in an order of 1,000-to-1 ratio. That is not easy. I can't think of off the top of my head any other field of engineering that has to deal with that kind of extremes and remain linear or constant or equal across that entire range. And so how did we do that in the old days? Well, we built devices that were really good in small areas and then built devices that were really good in other areas. So we had, subwoofers that were really good at the very lows and mid-range devices and high-frequency devices. And we tried to put all these together, and we sort of did. And they sort of worked, but not really. One of the things that I've been thinking a lot about recently is why the ear is just so darn tolerant of that blatant distortion. Why is it that we hear a recording of a guitar, let's say, and we know that the sound that emanates from that acoustic guitar comes from mostly of course, the strings and the bridge is moving and the top is moving and the whole thing is moving in a very complicated and dynamic way. But that movement, all of that movement, all those places the sound emanates from, that forms the acoustic signature of that instrument. Then we reproduce it over loudspeakers that completely destroy that. Where the highs come from a horn up here, which has its own directivity and its own issues. The mids might come from a device over here that has its own directivity and its own issues. And the lows would come from this subwoofer thing over here that has its complete set of issues. And there's absolutely no integration at all. And yet our auditory system says, yeah, that's a guitar. But does it really sound like a guitar? Yeah, sort of. Maybe it sounds more like a recording of guitar. Maybe we tolerate it because that's what we've come to tolerate. We accept it because we don't know anything better. And so over the years, we've learned to accept the fact that these loudspeakers are going to impart a certain amount of distortion, and we go, well, that's just the way it is. But at some point, the 60s hit, and, if you remember them, you probably weren't there, but that's another story. And what happened? Well, this revolution of music and big sound systems, and we had to get bigger and bigger and bigger and louder and louder and louder. Well, how do you do that? Well, you have to put more loudspeakers together because more is more, and we need more, and we need bigger. Well, then it became painfully obvious. And if you ever went to any of those shows, you remember that just putting loudspeakers together doesn't mean that they're going to work well together. And so you had these massive arrays of loudspeakers being built that really didn't sound that good, but they got awfully loud. And at some point, it was like, this still isn't quite working. Enter the era of the line array. Well, what did the line array do for us? Well, it certainly made a lot of people a lot of money. There's no question there. But it really wasn't an improvement over what I believe was the basic problem facing sound reproduction. How do you get the sound to emanate over this large range of wavelengths as if it had a single origin? That's the way we hear the sound. That's the way our ear brain mechanism is designed to hear it. Well, how do we reproduce that? The line array was not the solution. It, just like its predecessors, had an amazing amount of interference, of distortion, and so forth. It wasn't a big step forward, in my opinion. Now we come to the synergy horn. What does the synergy horn do for us? Well, in my view, the synergy horn is kind of like that holy grail of audio, if you will. It's one thing to take two woofers and put them sort of close together and say, okay, you guys play nice together. And if they're close within, we say a quarter wavelength, they will in fact play nice. They actually, acoustically and electrically, are well, they're not alive, but, if you'll pardon the anthropomorphism, they actually are aware of each other. And that can be shown experimentally. But it's extremely difficult, and until the synergy horn, there was no way to put high-frequency devices together, those devices which are large relative to the wavelengths they produce. It was very hard to put those together and make them play nice. And so the synergy horn is this remarkable invention that accomplishes a number of things. One, it accomplishes a nearly optimal transfer of energy from a mechanical domain to the acoustic domain. We call that acoustic loading. So by putting the woofers near the mouth of the horn, that's where they work the best. We put the mid-range devices further down the throat, that's where they work the best. In our first generation of synergy horns, we have a single compression driver at the throat. And so, like in our SH50, there's sort of three distinct components, if you will, each contributing in their own bandwidth, but relatively easy then to combine with a crossover back into effectively one source. And if we look inside this SH50, you see a number of important things. One, you see that the woofers are all within a quarter wavelength of each other and within a quarter wavelength of the apex of the horn. The same is true for the mid-range devices. And of course, the compression driver is then sitting at the apex. And as I said earlier, it's actually not that difficult to build a crossover which pulls these three elements into perfect alignment, and we do it with a passive crossover, by the way, such that when the wavefront leaves the speaker, we've maintained or created that integration that is, in my view, so important to quality sound reproduction. But if you look at this first generation synergy horn, you realize that there's one weakness. We can make really big ones, right? We can put, like our SH96 has 4 15-inch drivers all coupling into that same horn. That's a massive amount of low frequency potential. We've got a bunch of mid-range devices, but back at that apex, we still have that problem. How do you get more if you need more? You know, if you're at 10 and no, never mind. How do we take it to 11? Well, this was the next generation of the development of the synergy horn. Tom came up with this idea, or this technique for combining multiple compression drivers into the same horn. Now, unlike what a lot of our competition are doing, which they'll take multiple high-frequency horns and just put them very close together, which, by the way, doesn't really work, what we're doing is taking multiple drivers, putting them through a combiner, and combining their output seamlessly into the horn. And in some cases, actually shaping the bubble so that sound bubble, if you will, that wavefront, as it enters the horn, is appropriately shaped. Well, I've taken a lot of your time, and thank you for your attention. Thank you for considering Danley. Danley Sound Labs, no better sound. I'm Doug Jones.